Okay, looks like I got a bunch of questions here today from number 60. A real hard one, I realize. And you can see it's magenta, and I decided to print it because I wanted to look at this figure here and draw on it. Hopefully it would make more sense here. So let me read it, and it's a long problem, hard problem. It says here that a parallel plate capacitor with an area of L and W, so it has length here and width here. The plate is separated by a distance of T, okay. Region T has a region between the plates. It's filled with a wedge of two dielectric materials as shown. So we have this kappa 1 and this kappa 2. And that's what's going to make it kind of hard, this wedge shape here. It says, go ahead and assume T is much less than both the L and the W. That way we can kind of use our results for a infinite plate, and that's what we're going to do here. It says, A, determine the capacitance. And so here's kind of the strategy here. You might think of this as a little microscopic strip heading back into the paper. With a matching one on this side underneath, and then making a capacitor. And so this microscopic strip here, we might say has a length of dx. And it makes then a capacitance of maybe we'll say dc. Actually, let me call it dc sub s. You'll see the s here in a second. But let me point out then that you might view this then as another microscopic capacitor right next to it, and another one right next to it, and another one right next to it. And so if you have all these little strips going back, all of them make some kind of capacitance, and then all of them then would be in parallel with each other. And so maybe the place to begin here is to say, if you want to know the total capacitance, you would be adding up, and so there's my integration symbol, a bunch of microscopic capacitors that are made of these little strips going back. And so that's probably the first and most important conceptual picture first. Because then, if you look at one of these microscopic strips, and maybe I'll just do kind of a little, well, I was going to say cross-section, but maybe I'll kind of make it go back into the board there. Because it has some material of kappa, I'll put it here, 1 for a little bit. And I know it has a little wedge to it, but if it's microscopically thin, that's pretty much a straight line. And in the limit, it would be a straight line, and that's what we're going to eventually do here. And then below that would be some material of kappa 2, making the capacitor. And of course, this capacitor would go back a distance W. I kind of covered it up. And then, as I said, it has a thickness of dx. But the point I'm trying to get at here is then this little microscopic capacitor, which I called ds, would be like two capacitors in series. And so we draw a little line right here and say, well, there's a capacitance of kappa 1 and another one of kappa 2, and those two are in series. And so my d sub s, and now you see why I picked the s. The s is then saying this is the series. This is the result of these other little two microscopic ones in series. And so I'm adding up a bunch of microscopic ones, but this is made out of two microscopic ones. And so let me do the little formula for series. If we call this one above C1 and this one below C2, and maybe I should call it microscopic C1 and microscopic C2, then 1 over microscopic C1 plus 1 over microscopic C2 is equal to 1 over this microscopic with the sub s, and so this is what I was trying to say by the s, the series of those two. See, because now I could break this down into something that's actually doable. I could say, okay, how would I get the capacitance of this microscopic C1? And it's just a regular capacitor. Maybe you remember this formula, epsilon naught times area over D. Of course, that is what we derived for free space. So now we'd have to put a kappa in front of it to say, okay, this is the capacitance of a parallel plate capacitor. So I'm going to use that applied to this microscopic one. So this microscopic one would have kappa 1 for its capacitance. Then epsilon naught. The area then, it would be a length here, or maybe I should call that width for W, and then a thickness or a length of dx. And so that's what the area is equal to. Now, the separation here is a little interesting because it wouldn't be this whole thickness T, it's just this little piece. Well, let me do this. Let me say the lower half down here has a thickness of Y. So that means this upper half would have T minus Y. Okay, so I'll write this as T minus Y. And so we've got some thinking to do still about, well, Y would change as we go from different points, because ultimately we're going to do this step. Ultimately, we're going to say, what's the total capacitance? And we have to start with one over here. And at this point, I would say, this very first one, Y is really a 0. And then, of course, the T minus Y is T. And then by the time you get to the other side over here, a Y becomes a T. And then, of course, this thickness goes to 0. So it's a function. And we got to give that some thought process. But I think that's a good place to get started. And then you can also see the other little microscopic capacitor, C number 2, this one here. It's made out of a different material, so it would be kappa 2. Then it would be epsilon naught, and then it would be its width W, and then its length dx. And of course now its thickness, number 2 down here, would be just the Y. All right, so I'll call that page 2. Maybe that one's so obvious I don't need to number that one. But I have a feeling there's going to take quite a few pages here, and I will probably want to come back and forth. So let's keep going with this, because now if I write this as 1 over the microscopic capacitance, what I'll call in series, the first one is the reciprocal of C1. So here's C1. Let me take its reciprocal. So it would be T minus a W, and then a kappa 1, an epsilon naught, a width, and a dx. Add to that the reciprocal of capacitor number 2. All right. So put the Y in the top and the other one's in the bottom. So here is kappa 2, here's epsilon naught, here is the W, and there's the dx. And maybe I'll just notice that there are a couple of factors that certainly are the same here, and these 3 down here in the bottom. So I'll write it as 1 over epsilon naught W dx. And of course, then I'll be left with 2 fractions. This has a kappa 1 and a kappa 2. And maybe now it's time to deal with this Y here. So let me come back to page 1. And maybe do a cross-sectional drawing right here. Cut here. And so if we call this lower left-hand corner the origin, and so this is the x-axis and this is the y-axis, you can see that this wedge shape makes a line, and the equation for a line is y equals to mx plus b, where The m is the slope of the line, and the b is the intercept. And so this line right here has an intercept of 0, so that would just make an mx. And then the slope would be the rise over the run. So this has a height of t when it makes a run of L. So this would be t over Lx is equal to y. So there would be the mathematical connection between what we mean by y and where we are on the horizontal axis. And then that's what we need back here. The numerator of this second capacitor right here was the y. So let me write this as t over L times x. And then this one here would be t minus the y, which is a t over an L times an x. In fact, instead of writing a whole nother line, I can see with this compound fraction, I could really just move the L downstairs. Okay, so I'll just do that. And this might not be so obvious, but to get a common denominator, I could put an L over an L. And when I say common denominator, I mean of these terms in the numerator, not these two, although that's coming. But see, once this is a common denominator of L, I can put it downstairs and just erase that. So maybe the next line I will write will be this that says, all right, what is the common denominator of these two? And it looks like there's an L, a kappa 1, and a kappa 2. Because they each share an L and they each have a kappa 1 and a kappa 2. So to get this one, well, to get this one to the common denominator, I was multiplying by kappa 2. So I got to do the top by kappa 2. So this would be kappa 2 L over T minus kappa 2 Tx when I multiply each terms by kappa 2. And then this one, to get the common denominator, I have to multiply by kappa 1. So this would be kappa 1 Tx. All right. So that's what I have for the reciprocal of this little microscopic capacitor that's in series. So now if I flip it, I can get what I'm needing to do the integral. It's way back here, so I still got a lot of work to do. But I can now flip this, and so everything on the bottom becomes on the top, and so I'll just put this first. In fact, I'll put kappa 1, kappa 2, L first. Epsilon naught, the W dx. And then downstairs would be this piece. And knowing that soon I'm going to be doing an integral, let me put my x's stuff together. And so I'll leave this first term alone, kappa 2 LT, plus, and then looking at this, it looks like I've got a kappa 1 minus a kappa 2, kappa 1 minus kappa 2, a thickness, and an x. And so there would be my, what I guess I'd call the microscopic capacitor. So finally now I can do my integration. And so copying this original idea here down, the total capacitance of this very weird design, in fact I can't even think of a good practical reason why we would want something such as this, although maybe nature would result it. Maybe if we were geologists and we had overlapping rock sheets and we were using the capacitance as some way of measuring the density or the type of rock or the materials inside. Who knows? But I certainly know it's a good academic exercise, because if you could do this one, you're doing extremely well. This is not one that I would expect on an exam and be able to do in 25 minutes. Looking at my clock, I'm at 14 and a half minutes right now. So we got still a long way to go. So like I said, I wouldn't expect really for you to be able to be doing something quite this hard on an exam. All right, so now let's integrate this. So we've got the integral of, and we got kappa 1, kappa 2, L, epsilon naught, the width. There's that dx, that's good. Then there's this kappa 2, the L, the T, the plus, and we have kappa 1 minus kappa 2, a T, and an X. And so we're going to add it up by starting at, right here, X equals to 0, and go all the way until X equals to L. And fortunately, this is not a hard integral. It looks like we've got the X in the bottom, and it's linear, so we're going to have a natural log here. So I've got a kappa 1 and a kappa 2 and an L and an epsilon and a width. So I was pulling those out. But right here, it looks like this is a natural log of this kappa 2 LT plus kappa 1 minus kappa 2 TX. And then let me not forget all over, because of the chain rule, kappa 1 minus 2 over a T. So this is kind of your traditional U sub. I could, and I said this at least to some of you guys, if you had me for 121 and even in 123, is, actually I said it earlier, U subs are nice, and there are a lot of steps. I find E subs a little easier, just not even to do the U sub, just to kind of guess at it and then go back and take the derivative. And so I see this and that's chain rule. And so let me just check it. So I'll take the derivative. So if I took the derivative of ln of this mess would go downstairs. And good, that's exactly what I want. But then the chain rule would give me this little piece here on top, which is why I needed this one on the bottom to cancel that off and just be left with that. So good, that is the little piece I needed in my chain rule, which would be, showing up when I did a U sub. Now, let me not forget to put the limits of integration here. We're adding from 0 to L. So kappa 1, kappa 2, and I'm just going to put the L at the end so that the width and length, which represent the area of the sheet, are together there. And then this would be kappa 1 minus kappa 2, and its thickness T. And then I can put in my ln. And so if I put in ln with this L, watch what happens. Here's a kappa 2 LT plus, and with this multiplied out, this would be kappa 1 TL, and then minus kappa 2 TL. But there it is. Those two are going to end up canceling. And then technically it would be minus ln of 0, so that would be kappa 2 L over T. But a nice property of logarithms is when you subtract a natural log, you can put it down here as a quotient. So maybe I'll do that now. And I think, are we done? I thought there was going to be a little more. I know there's some more parts, B and C, so I know we're not completely done. But it looks like, yeah, we're done here, because this is going to be kappa 1 and then TL. And then minus, I'll write it as kappa 2 and another TL. And the T and the L cancel off. And we just end up with an ln of kappa 1 over kappa 2. And then, of course, all this other stuff, this epsilon and the length and the width and the kappa 1, kappa 2, and the difference between them and the thickness. Yay! And so there it is, the big piece. Although I see there's some more parts to this, so I'll keep going. So there's the answer to A, and maybe I'll come over here to page 3 and go, okay, let's move on to B. And so pulling page 1 here, looking at B, it says, should the capacitance be the same if the labels K1 and K2 are interchanged? Demonstrate that your answer does or does not have this property. Now, I'll start conceptually. I would think that if I had these materials interchanged, it would be really the same as if I just flipped it over like that. Yeah, and flipping it over, it doesn't change the capacitance. I mean, if I took a capacitor meter and I measured it like this, or I stood on my head and I measured it, I would get the same capacitance. So the symmetry of this and the physics of it tells me that I better get the same number. And then, of course, they're asking you to look at your answer. All right, so let's take a look at this answer that we got a moment ago in part A. And let me interchange them. Because if we did all of this again, but we had called kappa 2, the top piece, and kappa 1, the bottom piece, we would have gone everything through here, but kappa 1 and kappa 2 would have been just labeled in reverse. So what I'm going to say here is that if I had a capacitor that looked like this, so again, number 2 was in the top and number 1 was in the bottom, as opposed to what we just did, number 1 in the top and number 2 in the bottom, I would really go through all the same steps that I just did, but everywhere I would be calling something a kappa 1, I would call it a kappa 2. So I'll just change that in my final answer. And again, everything that I would be calling kappa 2, I would call kappa 1. So I'll just change that in my final answer. So that's what I would have gotten had it been the other way around. And so the question really is now, is this equal to that? And I would say, yes, it is. It may not be immediately obvious. I think this is immediately obvious, that kappa 2 times kappa 1 is the same as kappa 1 times kappa 2. So, okay, those are the same. But what stands out as not being the same is when you switch the order in a subtraction. You know, 5 minus 3 and 3 minus 5 aren't quite the same thing. In absolute value they are, but one's a positive and one's a negative. So maybe what I'll do, just to kind of prove to myself that this is the same as that, I'm going to rewrite the numerator in what it's still equal to. So I'll just change the order of those. And now it looks a little more like that. But I'll also do this. I'll pull out a negative sign and write it as kappa 1 minus kappa 2 over the thickness. Now, again, looking at this, I would say this doesn't yet quite look like that one because it's not only got a negative, but it's got the reciprocal of that. Which maybe now some of you are seeing it. A negative can be brought up there, which can then be also raised to the power of the natural log. So moving that negative over to here, I would have kappa 1 times kappa 2 epsilon naught times the L, the W, then the L, then this K1 minus this K2, then the T, and then I would have ln of K1 over K2. So this here does equal that when that is the same as that. So I would say yes, the math does show it. The math does show that you get the same thing when you interchange the material of kappa 1 and kappa 2. And so that was, I guess that wasn't too bad. It did have that little trickiness, if you will, with the properties of logarithms, and so you might not have seen it. This is going to be interesting, because in C it says show that if kappa 1 and kappa 2 approach equality, okay, so in other words, they begin to count the same, we'll just call it kappa, that your result should just be the same of a capacitor. So in other words, they should be this. Of course, we would have a T here, and the A would be the W times the L, but there it is, kappa, epsilon naught, the W, the L, and the T. And so in other words, if our material really isn't just two materials, it's one material. You can draw a line down the middle of it, but this equation, when you might say when K1 approaches K2, you know, what do you get for the total capacitance? All right, so let's take that limit, if you will. And so total capacitance is, and so you might say the limit as K1, or kappa 1, sorry, approaches kappa 2. actually the way they write it is they both approach just kappa. No 1 and no 2 anymore. Okay. So in the numerator, we would have really then a kappa squared. And in the denominator, here's where it's going to get a little hard. Because if you have a kappa 1 minus a kappa 2, and you take the limit that they both approach kappa, they're the same thing, now you get a 0 in the denominator. And then likewise, with a kappa 1 and a kappa 2 in the natural log, these approach each other. Kappa, that becomes 1, and the natural log of 1 is a 0 also. So, I need some thinking about this. And in fact, maybe I will write it this way, if this kind of helps. Let's call U equaling K1 over K2. And then we're going to say, let's take the limits as then U approaches 1. See, if we do that, we could do this. Take the limit as U approaches 1. And, of course, up here, we'll have this kappa squared, epsilon naught, the W, the L. And what I thought I would do is pull out maybe a K2, a kappa 2, so that this is kappa 1 over kappa 2 minus 1t. And then this is ln, kappa 1 over kappa 2. See, and that's where this kappa 1 over kappa 2 being defined as u can now be useful. So this would be kappa squared, epsilon naught, the w, the l. This K2 is going to become a kappa, so those are going to end up canceling. But then this is a u minus a 1 times a t over the natural log of a u. And I did all that so that I could really focus my attention on this. What is the limit as u approaches 1 of this stuff here? The natural log of u in the top and a u minus 1 in the bottom. And this is the trickiness of this one, because this is what you learned in your calculus class. You have a denominator that goes to 0, but you also have a numerator that goes to 0. The natural log of 1 is 0. So this is where L'Hopital's rule comes in. So let me take the derivative of the top and the bottom and take the same limit. So the derivative of ln of u is 1 over u, and the derivative of this would just be a 1. And that's easy to take the limit, because when u approaches 1, we just get 1 over 1 over 1, which is 1. So this whole mess, and maybe I can just squeeze it here at the end, this ln u over u, or u minus 1, this right here all goes to 1. And so we're just going to be left with a kappa, an epsilon naught, a w, an l over a t. And that's exactly what we said here. We started to see that we would expect to get if this was all one material, when kappa 1 and kappa 2 were exactly the same. Yay, I told you that was a long one. Yeah, 29 minutes. Nice.